Somewhere in Russia, buried beneath the frozen soil of the Vladimir region, archaeologists uncovered something that stopped them cold. It was not a weapon. It was not a tool. It was a child buried with such extraordinary care that even today, nearly 3 decades after the discovery was first fully analyzed, researchers still struggle to explain it. The skeleton belonged to a boy, no older than 12 or 13 years of age. He had been placed in the earth with deliberate, almost ceremonial precision, and surrounding his small body, carefully arranged across his clothing and woven into the fabric of whatever he once wore, were more than 3,000 beads carved from mammoth ivory. 3,000 beads, each one individually shaped, individually polished. Scientists who studied the site estimated that producing a single bead of this kind would have taken a skilled craftsman somewhere between 45 minutes and an hour. If you do the math, and you should, that is more than 2,000 hours of labor, just for the beads on this one child's burial. That is roughly 3 months of someone working every single hour of daylight, without pause, without rest, doing nothing except carving ivory beads for a boy who would never grow up. This is the Sunghir burial site. It sits about 180 miles northeast of Moscow. The remains date to approximately 28,000 years before the present day, and it is not simply a burial. It is a window. Because here is the question that archaeologists have quietly wrestled with since the site was first excavated in the 1960s by Soviet researcher Otto Bada. If these people were fighting to survive one of the most brutal climates in human history, if they were hunters moving through landscapes that made Siberia in January feel almost welcoming, if their entire waking existence was organized around not dying from the cold, from starvation, from predators, from exposure, then who had the time, the energy, the surplus labor, and the emotional architecture to spend 3 months carving beads for a dead child? The answer matters more than it might seem, because what Sunghir tells us is not just that ancient humans were capable of grief or beauty or symbolic thinking. We already suspected that. What it tells us is that 28,000 years ago, in the middle of the last glacial maximum, in a world that was objectively trying to kill every living thing on its surface, there existed communities with enough organizational complexity, enough social cohesion, and enough specialization of labor to invest thousands of hours in a funeral. That is not survival behavior. That is civilization behavior, and it is buried in frozen soil that most people will never visit, in a museum catalogue that most people will never read, speaking a language that most of us have simply never been taught to hear. This documentary is about learning to hear it. The last ice age, specifically the window known as the last glacial maximum, which reached its peak roughly 26,000 to 19,000 years before the present, was not a single event. It was not a season, or a storm, or a bad century. It was a planetary restructuring. Ice sheets more than 2 miles thick, pressed down across what is now Canada, northern Europe, and Siberia. Sea levels sat roughly 300 feet lower than they do today, exposing coastlines, land bridges, and entire subcontinents that have since slipped silently beneath the ocean. Average global temperatures were somewhere between 7 and 9 degrees Celsius colder than the world you and I were born into. The Sahara was not a desert. The Amazon was largely savanna. The British Isles did not exist as islands. Britain was physically connected to France and to Denmark by a vast low-lying plain that would eventually become the floor of the North Sea. This was the world that shaped us. Not the cities, not the writing, not the agriculture that followed thousands of years later. This, the ice, the cold, the migrations across impossible terrain, the decisions made in darkness around fires that had to be maintained, or everyone died. And yet here is the thing that keeps drawing researchers back to this period, the thing that makes the Ice Age not simply a chapter in a geology textbook, but one of the most profound unsolved puzzles in the entire history of human science. The people who lived through it were, in every meaningful biological sense, us. Their brains were the same size as ours. Their vocal anatomy was identical to ours. Their hands could do everything our hands can do. If you took a child from Sunghir 28,000 years ago and raised her in a modern city, she would learn calculus, she would compose music, she would write software. The hardware was fully assembled, which means every question we ask about Ice Age humans is, in a quiet and uncomfortable way, a question we are asking about ourselves. What is a human being capable of when everything is stripped away, when there is no safety net, no infrastructure, no emergency service, no hospital, no warm room to retreat to, when the landscape itself is trying to erase you? The answer, written in ivory beads and cave paintings and bone needles and human footprints pressed into volcanic ash 65,000 years deep, is both humbling and extraordinary, and it is largely buried, largely forgotten, largely unanswered. Before we go further, if you are watching this for the first time, welcome. This channel is dedicated to exactly this kind of story. The long, slow, strange history that lies beneath the history most of us were taught. If this is the kind of journey you want to take, consider subscribing and turning on notifications so you do not miss what comes next. There are 11 more parts to this story, and some of what follows will be even harder to explain than a child buried in 3,000 beads. Now, back to the ice. Over the next 2 hours, we are going to walk through 12 chapters of this frozen, dangerous, endlessly surprising world. We will look at the science of what the Ice Age actually was. Not just cold, but a living, pulsing machine with rhythms that operated on timescales of 10,000 years. We will look at what humans ate, what they wore, how they built shelters that could hold warmth against temperatures that would kill an unprotected person in less than 30 minutes. We will look at the continents that are now beneath the ocean, and what may have been lost when the water rose. We will follow the migrations across open ocean, across land bridges, through mountain passes that should have been impassable. We will sit with the questions that archaeologists have noted but not yet answered, the anomalies that do not fit cleanly into the standard model of human development, the places where the evidence points in a direction that most textbooks have not yet had the courage to follow. There are no invented mysteries in what follows. Every unanswered question you will hear about is genuinely, officially, academically unanswered. Every site is real, every researcher is real, every date comes from peer-reviewed science. The only thing that has been added is attention, because the truth of the Ice Age, what it was, what it demanded, and what it built inside the human species, is strange enough on its own. It does not need embellishment, it only needs to be heard. To understand what humans survived, you first have to understand what they were surviving. And this is where most popular accounts of the Ice Age quietly lose the thread. They show you a glacier. They show you a mammoth. They give you a temperature number and expect that to be enough. But the Ice Age was not a temperature. It was not even a single event. It was a system, a slow, grinding, planetary scale machine with its own rhythms, its own logic, and its own peculiar relationship with time that operates on a scale so vast it makes all of recorded human history look like a single afternoon. Let us start with the mechanism. In the 1970s, a team of scientists led by James Hayes, John Imbrie, and Nicholas Shackleton published a paper in the journal Science that is now considered one of the most important contributions to climate science of the 20th century. The year was 1976. The paper was titled, in the understated fashion of academic science, Variations in the Earth's Orbit, Pacemaker of the Ice Ages. What it confirmed, drawing on decades of deep-sea sediment core analysis, was something that a Serbian mathematician named Milutin Milankovic had proposed decades earlier, largely without acceptance, working through calculations by hand during the years of the First World War. The idea is this: Earth does not travel around the Sun in a perfectly stable, unchanging path. It wobbles, it tilts, it stretches, over long cycles, some running close to 100,000 years, some running roughly 41,000 years. Some running around 23,000 years. The shape of Earth's orbit shifts, the angle of Earth's axial tilt changes, and the timing of Earth's closest approach to the Sun drifts forward and backward through the calendar. These are the Milankovitch cycles, and when they align in certain combinations, they reduce the amount of summer sunlight hitting the northern hemisphere, just enough that winter snow does not fully melt. It accumulates, year after year, century after century. The ice builds. This is not a theory anymore. It is, in the language of science, essentially confirmed. What this means, practically, is that the Ice Age was not a single freeze. Over the last 2.5 million years, Earth has cycled through somewhere between 40 and 50 major glacial periods. In the last 500,000 years alone, There have been at least 5 distinct glacial maxima, 5 separate episodes during which massive ice sheets covered significant portions of the planet's northern landmasses. Modern Homo sapiens, who have been anatomically present for somewhere between 300,000 and 315,000 years depending on which fossil you are looking at, lived through the last 2 of these cycles. They did not step into a cold world. They evolved inside a world that was rhythmically, predictably, repeatedly becoming cold and then warming over timescales that dwarfed anything a single human life or a single human culture could perceive. Now let us talk about the ice itself. At the peak of the last glacial maximum somewhere around 26,000 years ago, sustained through roughly 19,000 years before the present, the planet carried approximately 2.5 to 3 times as much glacial ice as it does today. The Laurentide ice sheet covered essentially all of what is now Canada and extended well into the northern United States, pressing down with such immense weight that it depressed the crust of the Earth itself by hundreds of meters. Parts of Canada are still rebounding from that pressure today, slowly rising at rates of more than a centimeter per year, a process geologists call isostatic rebound. The Fennoscandian ice sheet covered Scandinavia, most of Britain, and large portions of northern continental Europe. Smaller ice caps sat over the Himalayas, over the Alps, over portions of East Africa at high elevation. If you had stood in what is now Chicago 20,000 years ago, you would have been standing beneath roughly 1 mile of solid ice. The consequences of this much locked water rippled through every system on Earth. Sea levels, as mentioned, dropped by approximately 90 to 120 meters relative to today. The precise figure varies depending on the specific point in the glacial cycle. 120 meters is roughly the height of a 40-story building. Every coastline on Earth shifted dramatically outward. The English Channel was a river valley. The Persian Gulf was largely dry land. The islands of Southeast Asia, Sumatra, Java, Borneo were the highland edges of a single enormous landmass that researchers now call Sunderland, a continent roughly the size of Western Europe that existed above the waterline for tens of thousands of years before being swallowed as the ice melted. Beringia, the land bridge connecting what is now Siberia to what is now Alaska, was not a narrow corridor. At its maximum extent, it was approximately 1,600 kilometers wide from north to south, larger than the modern state of Texas, larger than France and Germany combined. It was not a bridge in any landscape sense. It was a subcontinent, with its own plant communities, its own animal populations, its own internal weather patterns. People did not cross it in a season. Evidence from Bluefish Caves in the Yukon, analysed by Lauriane Bourgeon and her colleagues at the University of Montreal, and published in 2017, suggests humans were present in Beringia as far back as 24,000 years ago, meaning they may have lived on this now drowned land for thousands of years before the ice corridors opened and allowed movement further. South, Sunderland, Beringia, Doggerland. These are not marginal geographic curiosities. They are the buried homelands of real populations of real people, and they are, for the most part, inaccessible to archaeology. We will return to this problem at length in the next chapter, because the implications are significant in ways that the mainstream conversation about the Ice Age rarely acknowledges. But before we leave the mechanics of the frozen machine, there is one more phenomenon that deserves its own moment: Heinrich events. In 1988, a German marine geologist named Hartmut Heinrich was analysing sediment cores pulled from the floor of the North Atlantic when he found something he could not immediately explain. At regular intervals in the sedimentary record, there were layers of coarse-grained material rock fragments, gravel, debris sitting in sediment that otherwise contained only the fine particles that drift down slowly from surface waters. Rock debris does not drift. It sinks. The only mechanism that could carry coarse material to the middle of the North Atlantic and then drop it across a wide area was ice. Specifically, icebergs. What Heinrich had found were the signatures of catastrophic, episodic collapses of the Laurentide ice sheet events, during which enormous armadas of icebergs carved off the eastern coast of North America drifted across the North Atlantic, melted, and dropped their rocky cargo on the ocean floor. These events, now called Heinrich events, they flooded the North Atlantic with enough cold, fresh meltwater to dramatically slow, and in some models, temporarily halt the Atlantic meridional overturning circulation, the deep ocean current system that is responsible for redistributing heat around the entire planet. When that circulation slows, Europe cools rapidly. When Europe cools rapidly, drought spreads across North Africa and the Middle East. When North Africa dries, populations shift. When populations shift under pressure, culture changes. 6 confirmed Heinrich events have been identified in the last glacial period. Each one appears to have triggered cascading effects across multiple continents simultaneously, and what remains unexplained is the precise trigger mechanism, what caused the ice sheets to destabilize at those specific moments, and whether the intervals between events followed any predictable internal logic or were essentially random. This is not a settled question, it is an open one, and it matters because it means the Ice Age was not simply cold. It was dynamic. It pulsed. It breathed. It periodically reached out and rearranged the ecological and climatic conditions of half the planet within a human lifetime. The people living through it were not experiencing a stable frozen world. They were navigating a world in constant, slow, sometimes violently sudden transformation. The frozen machine was always running, and the humans caught inside it had no choice but to learn its rhythms, or disappear along with everything else. There is something quietly strange about sitting with this material, about reading through the sediment cores and the orbital mathematics and the Heinrich event layers, and realizing that the world these people inhabited was not a backdrop. It was a participant. It had moods. It had thresholds. It would hold steady for centuries, and then, within a single human lifetime, shift into something unrecognizable. If you are listening to this right now, wherever you are in the world, whether it is the middle of the night and the room around you is completely still, or early morning with the light just beginning to come through, or somewhere in the long, quiet hours between, take a moment and drop a note in the comments. There is something worth knowing about who gathers around stories like this one, and from how far across the world they come. This material has a way of finding the people who need it at exactly the right hour. And with that thought settled, we move forward, because the machine did not stop. There is a number worth holding in your mind as we begin this chapter. -40 degrees Celsius. At that temperature, exposed skin begins to develop frostbite in under 10 minutes. The moisture in your exhaled breath freezes before it fully leaves your body. Metal becomes brittle. Diesel fuel gels. The fat beneath your skin, which your body depends on as its primary insulation layer, begins to lose its effectiveness as a thermal barrier. At -40, a naked human being, healthy, well-fed, physically fit, has somewhere between 20 and 30 minutes before the physiological cascade toward death becomes irreversible. This was not an unusual temperature in glacial Europe. In Siberia and Central Asia, during the last glacial maximum, it was, in many regions, a fairly ordinary winter night. And yet the archaeological record is unambiguous. People were there, burying their dead there with carved ivory beads and ochre pigment and deliberate ceremony, generation after generation, in landscapes that by every physiological measure should have been uninhabitable for a species that evolved in the warmth of the African continent. So how, precisely, did they do it? The answer is not a single thing. It is a toolkit, and each component of that toolkit represents a cognitive and technical achievement that, when you examine it closely, is far less primitive than the word prehistoric tends to imply. Start with fire. The control of fire is so foundational to human survival in cold environments that it can be easy to take it for granted, to file it away as something ancient humans did without registering what it actually required. Fire is not simply warmth. Fire is a complete transformation of the human ecological niche. It extends the habitable day into darkness. It changes which foods can be consumed and how many calories the body can extract from them. It provides protection from predators. It enables the processing of materials hardening wood, drying hide, rendering fat that would otherwise be unavailable as resources. In 2012, a team led by Francesco Berna of Simon Fraser University published findings in the Proceedings of the National Academy of Sciences documenting evidence of controlled fire use at Wonderwork Cave in South Africa's Northern Cape. In province, the evidence burned bone fragments and plant ash found in a stratigraphic layer securely dated to approximately 1 million years before the present, pushed the confirmed record of fire use back further than many researchers had previously accepted. That is not Homo sapiens, that is Homo erectus, our direct ancestor, already managing combustion with enough consistency to leave a structured, repeatable signature in a cave floor. By the time of the last glacial maximum, fire management had become something considerably more sophisticated than a single hearth. At sites across glacial Europe and Siberia, archaeologists have found evidence of structured hearth arrangements inside dwelling structures, not one central fire but multiple coordinated heat sources, positioned to maximize warmth distribution across living and sleeping areas. This is not accidental, it is engineering, applied to the physics of heat retention in enclosed spaces. But fire alone cannot keep a human body alive at -40. For that, you need clothing. And not just any clothing. Tailored clothing, fitted, layered, constructed with enough precision to trap body heat against the skin while allowing moisture to move outward. The gap between wrapped animal skin and a genuinely tailored garment is not cosmetic, it is thermodynamic. A loosely draped hide leaves air gaps at the wrists, the neck, the ankles. In severe cold, those gaps are lethal. The difference in heat retention between the two is, in extreme conditions, the difference between survival and death. The evidence for tailored clothing in the Paleolithic is indirect but compelling. It comes primarily from needles, not the crude bone splinters you might imagine, but genuine eyed needles, thin, carefully shaped, with a precisely drilled aperture at one end through which thread could be passed. Needles of this kind have been found at Denisova Cave in the Altai Mountains of Siberia, associated with layers dating to somewhere around 50,000 years before the present. The Denisova cave needle, studied and reported by researchers at the Institute of Archaeology and Ethnography in Novosibirsk, is so finely made that when it was first recovered, it was initially assumed by some team members to belong to a more recent layer. It did not. It was exactly where the stratigraphy said it was. 50,000 years old, and indistinguishable in its basic design from a sewing needle you might find in a fabric store today. What this tells us is that by the time the last glacial maximum arrived, the humans entering it were not improvising their cold weather solutions. They had been refining textile and leatherwork technology for tens of thousands of years. The clothing they wore during the worst of the ice was the product of a long, accumulated, transmitted tradition of technical knowledge. Now we come to the component of the survival toolkit that tends to receive the least attention in popular accounts, possibly because it is the least visually dramatic, and yet it may be the most consequential of all. Fat. The human body, when operating in sustained extreme cold, requires a caloric intake that is almost incomprehensible by modern standards. Estimates for the daily caloric needs of an active human in genuine polar conditions, conditions comparable to glacial Europe during the LGM, run somewhere between 5,000 and 7,000 kilocalories per day. For context, the average recommended daily intake for a moderately active adult in the modern world is somewhere around 2,000 to 2,500 kilocalories. These people needed 2 to 3 times that amount every single day simply to maintain core body temperature while performing the physical work of survival. And the calories they needed were not primarily from carbohydrates. Carbohydrates metabolize quickly and efficiently, but do not sustain core temperature over extended cold exposure the way dietary fat does. The body needs fat, high-density, calorie-rich animal fat to fuel the sustained thermogenic processes that keep a human alive through a glacial winter. Populations living in Arctic and subarctic conditions today, such as the Inuit of northern Canada and Greenland, derive somewhere between 50 and 70% of their total caloric intake from fat. Researchers studying cold climate physiology have noted that below a certain threshold of dietary fat intake, sustained survival in polar conditions is simply not physiologically possible, regardless of how much total food is consumed. Which brings us to a remarkable site in the Czech Republic. Pavlov I, located in the South Moravian region and dated to approximately 26,000 years before the present, is one of the most thoroughly studied Gravettian occupation sites in Central Europe. Among its many features, excavations led by Jiří Svoboda of the Czech Academy of Sciences revealed large, purpose-built processing pits containing the fragmentary remains of mammoth bones that had been systematically cracked, crushed, and processed in a way that points unmistakably to one specific goal: the extraction of bone marrow and bone grease. Bone grease is made by boiling crushed bone fragments in water, skimming the rendered fat from the surface, and storing it. It is extraordinarily calorie-dense. It is shelf-stable in cold conditions. And at Pavlov I, the scale of this processing was not casual. It was industrial. The volume of bone material processed at this site, analyzed and documented by Svoboda's team over decades of excavation, suggests an organized, sustained, community-scale operation dedicated to fat extraction and storage. A prehistoric supply chain built entirely around the management of one critical nutrient. One mammoth, for reference, carried somewhere in the range of 2 to 3 million kilocalories in combined meat, organ tissue, and fat. A single animal, processed correctly and stored in the natural freezer of a glacial winter, could sustain a small group through weeks or months of conditions too severe for active hunting. The people at Pavlov I were not living hand to mouth. They were managing reserves. And yet there is a dimension to human cold adaptation that goes beyond tools and techniques, beyond needles and hearths and bone grease pits. One theory, grounded in research on modern populations with deep ancestry in cold climate environments, suggests that Ice Age humans may have undergone genuine physiological adjustments at the genetic level, not dramatic enough to be called speciation, but measurable enough to show up in population genetics. Studies on the Yakut people of northeastern Siberia, whose ancestors have occupied some of the coldest permanently inhabited territory on Earth for thousands of years, have identified specific gene variants associated with altered fat metabolism, modified thermogenesis, and changed vascular response to cold that appear to have been subject to positive selection. These adaptations did not emerge in a generation. They accumulated over thousands of years of life in exactly the kind of environment we are describing. Whether the Gravettian and Aurignacian peoples of glacial Europe and Siberia were similarly adapted at the genetic level is not yet confirmed. The ancient DNA studies required to answer that question are ongoing, but the question is being asked seriously by serious researchers in peer-reviewed contexts. What the full toolkit reveals, when you lay it out this way: fire management, tailored insulating clothing, industrial-scale fat processing. Possible physiological adaptation is not a picture of desperate, barely surviving primitives clinging to existence at the edge of a hostile world. It is a picture of mastery, incomplete mastery, certainly. People still died from cold, from starvation, from the thousand ordinary and extraordinary hazards of a glacial landscape, but the system they built to survive was coherent, sophisticated, and demonstrably effective across thousands of years and millions of square kilometers of terrain that had no business supporting human life at all. The body that walked out of Africa was not built for the ice, but the mind that came with it built something that was. Picture a map of the world as it exists today. Now, slowly drain the oceans. Watch the coastlines creep outward. Watch shallow seas become plains. Watch islands merge into peninsulas, peninsulas merge into continents, and familiar blue expanses become something altogether different: rolling lowland terrain, river valleys, wetlands, forests, places where animals grazed and rivers ran, and, almost certainly, where people lived their entire lives without ever knowing that one day the ground beneath their descendants' feet would lie 300 feet beneath the surface of the sea. This is not a thought experiment. It is geography. It is what the world actually looked like during the last glacial maximum, and for tens of thousands of years before and after it. The world map most of us grew up with, the one with those familiar coastlines. Those recognizable continental shapes, is a portrait of a planet with unusually high sea levels. It is the exception, not the rule. For most of the last 100,000 years, the Earth looked different. Significantly, fundamentally different. And the implications of that difference for our understanding of where ancient humans lived, what they built, and what traces they left behind are still being quietly processed by the scientific community. Let us begin with the most thoroughly documented of these drowned worlds, Doggerland. Today, If you sail from the eastern coast of England toward Denmark or the Netherlands, often rough body of water sitting at an average depth of roughly 90 to 95 meters, during the last glacial maximum and for thousands of years following the initial warming, that water was not there. In its place was a vast, low-lying plain connecting Britain to continental Europe, a landscape of river systems, marshland, forests, and open grassland that supported dense populations of animals and, almost certainly, substantial communities of hunter-gatherers and later early farmers. Researchers named it Doggerland, after the Dogger Bank. The shallow sandbank in the central North Sea where fishing trawlers have for over a century been accidentally pulling up not just fish but bones, mammoth bones, aurochs bones, the antlers of giant deer, and occasional fragments of worked wood and shaped stone that can only have come from human hands. The University of Bradford's Europe's Lost Frontiers project, running from 2017 through 2022 and led by Professor Vince Gaffney, applied seismic survey technology, sediment core analysis, and environmental DNA sampling to systematically map what Doggerland actually looked like and what it contained. The results pushed the conversation well beyond the anecdotal. The project identified preserved river channels, lake basins, and what appear to be former wetland environments of extraordinary ecological richness, exactly the kind of landscape that hunter-gatherer populations consistently preferred and consistently occupied at high density wherever it appeared on Earth. Doggerland was not marginal terrain, it was prime real estate, and it began its final submersion somewhere around 8,000 years before the present, with a catastrophic acceleration triggered in part by a massive submarine landslide off the coast of Norway, the Storegga Slide, which sent a tsunami across the remaining low-lying areas of the plain and may have severed the last land. Connection between Britain and the continent within living. Memory of the people who witnessed it. Those people left no written record. Their settlements are underwater, their middens silted over, their paths and hearths and structures buried beneath a century of accumulated marine sediment for every 1,000 years since the flooding. The archaeologists working on this problem are not dealing with inaccessible ruins in the romantic sense. They are dealing with a systematic, planetary-scale erasure of the coastal record, not through any deliberate concealment, but through the simple, indifferent mechanics of rising seawater. Now move east, far east. During the last glacial maximum, the islands we now call Sumatra, Java, Borneo, and the Malay Peninsula were not islands. They were the elevated interior highlands of a single continuous landmass, stretching from the Asian mainland southward into what is now the Java Sea and the South China Sea. This landmass, Sunderland, was approximately 2 million square kilometers in extent at its maximum. To put that in terms that register, that is larger than the entire Indian subcontinent. It had river systems longer than the Rhine. It had interior plains, coastal estuaries, and the kind of diverse, resource-rich tropical environment that has supported human populations at high density everywhere it has appeared on Earth. Robert Foley of Cambridge University and other mainstream quaternary scientists have confirmed the basic geographic and ecological reality of Sunderland without controversy. The landmass existed. It was habitable. It was almost certainly inhabited, given everything we know about human migration patterns along the southern coastal route out of Africa. What is less clear, what remains a genuinely open question in the scientific literature, is the density and complexity of whatever populations lived there and what happened to their material culture when the waters rose. The sea level increase that swallowed Sunderland was not instantaneous. It unfolded over several thousand years following the end of the last glacial maximum, punctuated by episodes of more rapid flooding during meltwater pulses. Everything that existed at or near sea level on that landmass is now underwater, in tropical conditions that are among the least favourable on Earth for the preservation of organic material. One theory, proposed seriously by researchers working in historical genetics and quaternary geography, suggests that the coastal and lowland populations of Sunderland may represent a significant missing chapter in the story of human migration and early cultural development in Southeast Asia and the Pacific, not because their existence is disputed, but because the physical evidence of their lives now sits beneath an average of 50 to 80 meters of ocean water across a survey area larger than most countries. This is not a suppressed history. It is a drowned one. The distinction matters. There is a version of this conversation that exists in popular culture, books, documentaries, online discussions that frames the drowned landscapes of the Ice Age as evidence of deliberate concealment, of established archaeology, protecting a false timeline, of institutional resistance to uncomfortable truths. That framing, whatever its entertainment value, does a disservice to the actual situation, which is in many ways more interesting. The real problem is not concealment. It is difficulty. Underwater archaeology is expensive, technically demanding, and methodologically constrained in ways that terrestrial archaeology is not. The equipment required to survey, excavate, and recover material from sites sitting 60 or 80 meters below the ocean surface did not exist in practical form until the last few decades. The Europe's Lost Frontiers project represents the current frontier of what is technically achievable, and it required a multi-million-euro budget and 5 years of work to produce a partial map of one drowned landscape. There are dozens of others waiting. Which brings us to a site that sits in a different category from Doggerland and Sunderland. Not a submerged plain, but a structure, sitting in shallow water off the southern coast of Japan that has generated genuine scientific disagreement for nearly 40 years. The Yonaguni Monument. Discovered by a sport diver named Kihachiro Aratake in 1986, the Yonaguni Monument is a series of large, flat-topped rock formations sitting at depths of between 5 and 27 meters off the coast of Yonaguni Island in the Ryukyu chain, the southernmost islands of Japan. The formations include wide, stepped terraces, vertical faces, and a series of what appear at certain points to be precisely right-angled corners and flat platforms. Masaaki Kimura, a marine geologist at the University of the Ryukyus, who spent years diving the site and documenting its features, argued that the regularity of certain structural elements, particularly the right angles, the flat upper surfaces, and what he interpreted as carved channels and post holes, was inconsistent with purely natural erosion and indicated human modification during a period when the site was above water, which the local sea level record places at approximately 10,000 or more years before the present. The mainstream geological response, offered by researchers including Robert Schoch of Boston University, who also personally dived and examined the site, is that the monument is a natural sandstone formation shaped primarily by erosion along the parallel joint systems that run through the rock. A process that can, in the right geological conditions, produce remarkably regular angles and flat surfaces without any human involvement. Schoch's position is that the natural explanation is sufficient. Kimura's position is that it is not. What remains unexplained, and what keeps this site in the legitimate scientific conversation rather than in the purely fringe category, is the precise geometric regularity observed at specific points in the formation that Japanese marine geologists who have examined the raw survey data have described as statistically unusual even for highly jointed sandstone. The debate is real. The site is real. And the question of whether any portion of it reflects human activity during a period when it was accessible above sea level has not been definitively closed in either direction. That uncertainty is not a failure of science. It is science doing exactly what it is supposed to do, holding a question open until the evidence is sufficient to close it. What the drowned worlds of the Ice Age ultimately represent, taken together, is a simple and rather profound problem of sampling. The archaeological record that forms the basis of everything we think we know about prehistoric human behavior and settlement is not a complete record. It is not even close to a complete record. It is the portion of the record that happened to survive above the waterline, in conditions favorable to preservation, in locations that modern researchers have had the resources to investigate. The rest is still out there, slowly settling into the silt, waiting beneath water that was once, for people whose names we will never know, simply the ground beneath their feet. The last woolly mammoth died on an island, not 10,000 years ago, in the deep prehistoric past that feels safely distant from anything resembling human history, not alongside the cave lions and the giant ground sloths in some ancient, unimaginable twilight. The last known population of woolly mammoths, a group of dwarf individuals that had been isolated on Wrangel Island in the Arctic Ocean north of Siberia, survived until approximately 4,000 years before the present. That is roughly 1,700 years before the Common Era. The pyramids at Giza were already standing. The Bronze Age was well underway across the Middle East and the Mediterranean. Somewhere in what is now Iraq, the earliest known law codes were being written down on clay tablets, and on a remote Arctic island, the last mammoths were still alive. This fact, confirmed through radiocarbon dating and genomic analysis by Love Delen and his colleagues at the Swedish Museum of Natural History, has a quality that is difficult to absorb the first time you genuinely sit with it. We did not miss the mammoths by 10,000 years. We missed them by 4,000. In the span of recorded human civilization, the civilization of writing, of cities, of organized states and agricultural surpluses, and monumental architecture, woolly mammoths existed on this planet. They were simply on an island no one was visiting. When the Wrangel Island population finally disappeared, it did so not with a dramatic extinction event, but with the slow, genomic unraveling of a population that had become too small and too isolated to sustain healthy genetic diversity. Dalen's team, analyzing the genomes of multiple Wrangel Island individuals across different time periods, found accumulating evidence of inbreeding, of the gradual fixation of mildly harmful mutations, of a population quietly collapsing under its own genetic weight. They died, in the end, not from spears or from cold, but from the compounding biological cost of isolation. But that is the last chapter of the mammoth story. The main question, the one that has occupied paleontologists and archaeologists and evolutionary biologists for more than half a century, concerns the broader extinction. Why did the woolly mammoth, the woolly rhinoceros, the cave lion, the Irish elk, the giant ground sloth, the short-faced bear, the American mastodon, the Pleistocene horse, the giant beaver, and dozens of other large animal species disappear from the Earth within a geologically brief window between roughly 15,000 and 10,000 years before the present? This is not a simple question, and the history of how scientists have tried to answer it is itself a story worth telling. In 1966, an American ecologist named Paul S. Martin published a paper that detonated like a slow-burning charge through the paleontological community. Martin's argument, which he would spend the next 4 decades refining and defending, was direct and deliberately provocative. Humans killed the megafauna, not climate, not disease, not cosmic catastrophe. Specifically, the arrival of anatomically modern Homo sapiens in previously uninhabited continents, North America, South America, Australia, brought with it a predator that the local megafauna had never encountered and had therefore never developed behavioral responses to avoid. The animals, in Martin's model, were naive. They did not flee. They did not recognize the threat. And human hunters, equipped with projectile weapons and coordinated hunting strategies, moved through these populations with devastating efficiency, an extinction wave traveling at the pace of human migration across a continent. Martin called it the overkill hypothesis. And it was, from the moment of its publication, contested. The primary objection was geographical and temporal. If human predation was the driver, why did African megafauna survive? African animals had been living alongside increasingly sophisticated human hunters for 2 million years or more. By the time behavioral modernity was fully established, African megafauna had co-evolved alongside human predation pressure for long enough to develop appropriate fear responses and population resilience. The naive prey model works for Australia and the Americas, where human arrival was sudden and geologically recent. It works less cleanly for Eurasia, where humans and megafauna had coexisted for hundreds of thousands of years before the extinctions occurred. The competing explanation, climate change, had its own set of problems. The warming that followed the last glacial maximum was real, significant, and ecologically disruptive. Grassland steppe ecosystems that had sustained massive herbivore populations across Siberia and Central Asia shrank as forest expanded northward. The specific plant communities that woolly mammoths and woolly rhinoceroses depended on contracted rapidly as temperatures rose and precipitation patterns shifted. Ice Age megafauna were, in many cases, cold-adapted specialists, animals whose physiology and dietary requirements were calibrated for conditions that were disappearing. A warming world was not simply uncomfortable for them. It was, in the most literal ecological sense, erasing their habitat. But the climate argument also faced a fundamental challenge. The current warming period, The Holocene was not the first interglacial that these animal populations had experienced. Mammoths and many of their contemporaries had survived multiple previous warming cycles, including some that were as warm or warmer than the Holocene optimum. They had contracted and expanded with the ice before. What was different this time? The answer that has emerged from the most rigorous recent work is neither overkill nor climate alone. It is both, operating in combination, with each factor amplifying the vulnerability created by the other. A landmark analysis published in Nature in 2020 by a team including Tyler Murchie, Hendrik Poinar, and other researchers from multiple institutions applied ancient environmental DNA extracted from permafrost sediment cores to reconstruct the actual timeline of megafauna population decline across Siberia and the Arctic. What the data showed was a pattern of regional extinctions that correlated not cleanly with either human arrival or climate transition alone, but with the specific intersection of the two moments when human population pressure coincided with periods of rapid habitat fragmentation driven by climate change. Neither factor alone appears to have been sufficient across all regions. Together, they created a vulnerability cascade from which populations could not recover. This synthesis position represents the current mainstream scientific consensus. It is not a dramatic conclusion. It lacks the clean narrative satisfaction of a single villain, but it is where the evidence, taken seriously across multiple lines of inquiry, consistently points. And yet, there is a third hypothesis that sits at the edge of the mainstream conversation, supported by a body of peer-explanations evidence that is large enough and consistent enough to have refused to disappear despite 2 decades of skeptical scrutiny. In 2007, a team led by Richard Firestone of Lawrence Berkeley National Laboratory published a paper in the Proceedings of the National Academy of Sciences, proposing that a cosmic impact event, a fragmented comet or asteroid encountering Earth's Prydic atmosphere, occurred approximately 12,900 years before the present, triggering a rapid return to near-glacial conditions known as the Younger Dryas, and contributing significantly to the megafauna extinctions and the simultaneous collapse of the Clovis culture in North America. The evidence cited included elevated concentrations of platinum and iridium elements rare in Earth's crust, but common in extraterrestrial material in sediment layers corresponding to the Younger Dryas boundary at sites across North America, Europe, and the Middle East. It included microspherules and nanodiamond particles consistent with high-temperature, high-pressure impact events. It included a layer of black carbon interpreted as evidence of continent-scale wildfires. The hypothesis was, and remains, controversial. Multiple research groups have failed to replicate specific elements of the evidence at specific sites. Others have confirmed the anomalous platinum and nanodiamonds at different locations. A substantial review paper, published in the Journal of Geology in 2018, authored by a large consortium of researchers including James Kennett of the University of California, Santa Barbara, presented what the authors described as the most comprehensive stratigraphic confirmation of the impact markers to date, covering sites on 4 continents. What remains unexplained is the coincidence, if coincidence, it is of multiple simultaneous events at the Younger Dryas boundary. The abrupt climate reversal, the megafauna extinction pulse, the disappearance of the Clovis archaeological culture, and the anomalous geochemical markers appearing across widely separated sites on multiple continents at the same stratigraphic horizon. Each of these could potentially be explained independently. The challenge is explaining all of them together without invoking a common cause. The scientific community has not reached consensus on the Younger Dryas impact hypothesis. It has not been accepted, and it has not been conclusively refuted. It occupies, for now, the productive and uncomfortable space of a serious proposition that the evidence has not yet been sufficient to resolve, which is, in a way, the most honest place for it to be. What the full megafauna story leaves us with is not a solved case but a layered one. Human pressure, climate disruption, possible cosmic intervention, genetic isolation, different factors operating at different scales, in different regions, at different moments, in a process that unfolded across several thousand years and erased creatures that had survived on this planet for hundreds of thousands. The mammoths did not go quietly, and the world they left behind emptied of its giants, reshaped by warming and flooding and the slow advance of forest over grassland was the world in which everything that followed would have to find its footing, including us. On the 3rd of December, 1994, 3 cavers descended into a narrow limestone shaft in the Ardèche region of southern France, and found themselves standing in a gallery that no human being had entered in approximately 36,000 years. Jean-Marie Chauvet, Eliette Brunel, and Christian Hilaire had been exploring the cave systems of the region for years. They were experienced. They knew what old caves looked like, what they smelled like, how the sediment behaved underfoot in chambers that had been undisturbed for centuries. But nothing in their combined experience had prepared them for what their headlamps revealed as they moved deeper into the passage. The walls were covered, not scattered, not decorated in the casual, opportunistic way that suggested an individual who had paused in passing and pressed pigment to stone. The walls were covered with deliberate, confident, compositionally sophisticated images of animals: cave lions, woolly rhinoceroses, mammoths, horses, bears rendered with a command of line and form and perspective that art historians, when they eventually examined the photographs, initially refused to believe could be as old as the geological evidence suggested. Some of the figures used shading. Some used the natural contours of the rock surface to create the illusion of three-dimensionality, so that a bulge in the limestone became a shoulder, a hollow became the shadow beneath a jaw. One panel depicted a group of lions in what appeared to be a hunting formation, not individual animals placed side by side, but a scene, a composition, with implied movement and spatial relationships between the figures. The cave would become known as Chauvet Cave. The images would be confirmed through multiple independent dating methods to be approximately 36,000 years old, making them, at the time of their discovery, the oldest confirmed figurative art on Earth. For a while, that record stood. Then, in 2019, a paper published in the journal Nature by Maxime Aubert of Griffith University in Australia and his colleagues reported uranium series dating results from a cave on the island of Sulawesi in Indonesia. The site, known as Liang Bulu Sipong 4, contained figurative paintings, a hunting scene depicting warty pigs and dwarf bovids being pursued by figures that appeared to combine human and animal characteristics that the dating results placed at a minimum age of 45,500 years before the present. 45,500 years, older than Chauvet, older than any previously confirmed figurative art anywhere on Earth, and located not in Europe, where the tradition of Paleolithic cave art had long been assumed to have originated, but in Southeast Asia, in a cave on an island that sits on the eastern edge of the Wallacean archipelago, well beyond the continental shelf of Sunderland. The implications of this single result rippled outward in ways that the field is still absorbing. If the oldest known figurative art is in Sulawesi, then the assumption that symbolic and representational artistic thinking developed in Europe or spread outward from a European origin point is no longer defensible. The capacity for figurative art was either present in the common ancestral population that left Africa before the split between the lineages that eventually settled Europe and Southeast Asia, or it evolved independently in multiple locations. Either possibility fundamentally changes the story of when and where the human mind became the kind of mind that makes images of the world it inhabits. But the cave art story is not only about individual sites and their dates. There is a pattern running through the entire body of Paleolithic image-making that deserves its own careful attention, because it points towards something considerably more organized than a collection of isolated artistic impulses scattered across time and geography. Beginning in the early 2000s, a researcher named Genevieve von Petzinger, then working toward her doctorate at the University of Victoria in British Columbia, began systematically cataloguing not the figurative images in Paleolithic cave art, the animals, the hunting scenes, the human figures, but the geometric signs, the dots, lines, triangles, spirals, crosshatches, and abstract forms that appear alongside or independently of the figurative imagery across cave sites throughout Europe, Africa, and beyond. What von Petzinger found, after compiling data from 52 sites across multiple continents spanning a period from roughly 10,000 to 40,000 years before the present, was that the geometric signs were not random. They were not individual, site-specific inventions. Across all the sites she analyzed, she identified 32 distinct geometric forms that appeared repeatedly the same shapes, rendered in the same basic way, appearing in caves separated by thousands of kilometers and tens of thousands of years. 32 signs. Consistent, recurring. What remains unexplained is what this consistency means. Von Petzinger has been careful in her published work not to overstate the case. She does not claim these signs constitute a writing system in any modern sense. But she does argue, in her book The First Signs and in peer-reviewed papers, that the consistency and distribution of these forms is most plausibly explained by their representing a shared symbolic vocabulary. A set of conventional marks whose meanings were transmitted culturally across generations and across geographic distances, not invented fresh at each location, but carried, remembered, taught. If that interpretation is correct, then what we are looking at across the cave art sites of the Paleolithic is not a collection of independent artistic traditions, but something resembling a network, a system of shared symbolic communication that persisted with remarkable stability across timescales that make the entire history of writing look brief. And then there is the question of what, specifically, some of these images were communicating. In 1997, a German researcher named Michael Rappengluck, working toward his doctorate at Ludwig Maximilian University of Munich, published an analysis of the famous Hall of the Bulls at Lascaux Cave in the Dordogne region of France. The Hall of the Bulls, with its sweeping painted ceiling covered in horses, aurochs, deer, and abstract signs, is dated to approximately 17,000 years before the present, and is among the most studied and reproduced examples of Paleolithic art in existence. Rappengluck's analysis focused on a specific cluster of dots associated with one of the painted figures, a wounded bison positioned beneath a grouping of 6 dots, arranged in a pattern that Rappengluck argued corresponded to the Pleiades star cluster, as it would have appeared in the Écomber, glacial era sky. The Pleiades hypothesis has not been universally accepted. There are researchers who find the correspondence convincing and those who find it coincidental. What keeps it in the legitimate scientific conversation, rather than in the category of pure speculation, is that it is not the only proposed instance of astronomical encoding in Paleolithic imagery. The field of archaeoastronomy has accumulated a modest but growing body of work, suggesting that Ice Age humans were careful, sustained observers of celestial patterns, not surprisingly, given that the night sky in a world without artificial light would have been an overwhelming presence in daily and seasonal life, and that tracking celestial cycles would have had direct practical value for migration timing, seasonal hunting calendars, and navigational orientation. Archaeologists have noted one feature of the Paleolithic cave art record that tends to receive less attention than the remarkable images themselves: the near-total absence of interpersonal violence in the imagery. Across tens of thousands of individual images spanning 35,000 or more years of human image-making, scenes depicting humans attacking or killing other humans are extraordinarily rare, to the point of being essentially absent from the Paleolithic record. Animals are hunted. Humans are depicted in relation to animals, but the imagery of warfare, raid, massacre, and the kind of organized violence that dominates so much of the historical and even the Neolithic archaeological record simply does not appear. Whether this absence reflects a genuine characteristic of Ice Age, social life bands too small and too dispersed to sustain the kind of group-against-group violence that settled, resource-competing communities develop, or whether it reflects a convention of representation that excluded violence from the contexts in which images were made, is not resolved. Both possibilities have been seriously proposed by researchers working in Paleolithic social archaeology. Neither has been conclusively demonstrated. What the cave art record does demonstrate, taken as a whole across its full geographic and temporal extent, is that the humans of the Ice Age were not simply surviving their world. They were interpreting it. They were encoding it in durable form, in locations chosen with apparent deliberateness, using conventions stable enough to persist across thousands of years and thousands of kilometers. Chauvet in France. Lascaux in France, Altamira in Spain, Blombos Cave in South Africa, where ochre engravings 75,000 years old were documented by Chris Henshelwood of the University of Bergen, Liang Bulu Sepong in Sulawesi, Apollo 11 cave in Namibia. These are not isolated moments of individual creativity. They are nodes in something larger, a long, slow, distributed conversation conducted in pigment and engraved stone across the full span of what it means to be human. The network was ancient before writing existed, and some of what it was transmitting we still do not fully understand. In 2010, a small bone fragment sitting in a museum drawer in Novosibirsk changed the entire map of human prehistory. The fragment was a distal manual phalanx, the tip of a pinky finger, recovered from Denisova cave in the Altai Mountains of southern Siberia. During excavations in 2008, it was small enough to hold between two fingers. It had no distinguishing morphological features that would have marked it as anything other than a generic hominin bone fragment, the kind of material that accumulates in sediment layers at sites with long occupation histories and often sits in storage for years before anyone gets around to analyzing it properly. Svante Pääbo's team at the Max Planck Institute for Evolutionary Anthropology in Leipzig got around to it. What they extracted from that finger bone was mitochondrial DNA of such unexpected genetic character that when the results came back, the team ran the analysis again. And then again, the genetic sequence did not match Homo sapiens. It did not match Neanderthals, whose genome Pääbo's lab had been painstakingly reconstructing for years. It matched something else entirely, a population that had diverged from the common ancestor of both Neanderthals and modern humans somewhere between 300,000 and 400,000 years before the present, and had apparently been living in Asia, largely invisible to the fossil record, for hundreds of thousands of years. They called them Denisovans, after the cave where the finger bone was found. In the 14 years since that initial publication, the total physical fossil evidence for Denisovan existence has expanded to include portions of a jaw found on the Tibetan plateau, several isolated teeth from Denisova cave itself, and a handful of additional fragmentary remains. That is the complete physical record for an entire branch of the human family that ranged across a geographic area, potentially spanning from Siberia to Southeast Asia, across a time period measured in hundreds of thousands of years. The physical evidence that survives above the waterline and in conditions favorable to bone preservation amounts to material you could fit in a small envelope, and yet we know they existed. We know this not primarily from their bones, but from their DNA specifically, from the DNA they left inside the living populations of people alive on Earth today. This is the part of the story that tends to stop people. If you are of European or Asian descent, somewhere between 1.5% and 4% of your genome was inherited from Neanderthals. This is not metaphor. It is not ancestry in some loose cultural sense. It is actual nucleotide sequences passed down through every generation between a specific moment of interbreeding somewhere in Eurasia, between 40,000 and 60,000 years before the present, and the moment you were conceived, that trace their origin to individuals who belong to a different species of the genus Homo. Pääbo's team confirmed this in 2010, when they completed the first draft sequence of the Neanderthal nuclear genome and compared it against modern human populations from around the world. The signal was unambiguous. Eurasians carry Neanderthal DNA. Sub-Saharan Africans, whose ancestors did not pass through the geographic zones where Neanderthal populations lived, largely do not. For Denisovans, the picture is different and in some ways more striking. Populations in Melanesia, Papua New Guinea, the Solomon Islands, the indigenous peoples of Australia carry between 4 and 6% Denisovan-derived DNA in their genomes. Some populations in the Philippines carry even higher proportions. Tibetans carry a specific Denisovan gene variant, EPAS1, that provides measurably improved physiological tolerance for the low oxygen conditions of high-altitude living. This variant is so effective that it has been under strong positive selection in Tibetan populations since at least the time of their divergence from Han Chinese ancestry. Without it, sustained high-altitude habitation at the elevations where Tibetan communities have lived for thousands of years would be substantially more physiologically costly. A gene that helps humans breathe on the roof of the world, inherited from a species we did not know existed until 15 years ago. What remains unexplained is the full geographic range of the Denisovans and what their presence across that range actually looked like. The genetic evidence implies a population distributed from the Altai Mountains of Siberia, where Denisova Cave sits all the way to the islands of Wallacea and possibly into Australia, given the proportions of Denisovan-derived DNA in Melanesian and Australian Aboriginal genomes, the distance from Denisova Cave to Papua New Guinea is approximately 9,000 kilometers. For that genetic signal to be present at those proportions in those populations, Denisovans must have been present somewhere along the migration routes that ancestral Melanesians and Australians travelled, which means somewhere in Southeast Asia, possibly including the Sunderland landmass that was above water during the relevant period. One theory, proposed by researchers working at the intersection of ancient genomics and quaternary geography, suggests that the Denisovans were not a small, localized population confined to a few cave systems in Siberia, but a widespread, ecologically diverse group that had adapted to a range of environments across the Asian continent over hundreds of thousands of years. The extreme scarcity of their physical fossil remains may reflect not a small or geographically restricted population, but simply the conditions of preservation, the same bias toward cave sites in temperate zones that skews the entire Paleolithic record toward northwestern Eurasia and away from the tropical and subtropical environments where much of the relevant action may have been taking place. The story becomes still more complicated when you add the third major player. Neanderthals had been known to science since the mid-19th century, when the first recognized specimen was recovered from the Neander Valley in Germany in 1856. For most of the subsequent century and a half, the dominant narrative positioned Neanderthals as a failed evolutionary experiment. Stocky, heavy-browed, cognitively limited relatives who were outcompeted and replaced when modern humans arrived in Europe, roughly 45,000 years before the present. This narrative was tidy. It was also the genomic revolution dismantled it systematically. Neanderthals buried their dead, not merely placing bodies in convenient locations, but in some cases, including grave goods, flowers possibly, deliberate body positioning, and in the case of the Shanidar cave burials in the Kurdistan region of Iraq, excavated by Ralph Selecki beginning in 1951, arrangements that have been interpreted as evidence of structured funerary ritual. Though this interpretation remains debated, Neanderthals created pigment-based body decoration. They fashioned jewelry from eagle talons and raptor feathers, evidence recovered from sites in Spain and Croatia and analyzed by João Zilhão of the University of Barcelona. They made adhesive compounds from birch bark tar through a process that required controlled, multi-stage heating, a procedure so technically demanding that experimental archaeologists have struggled to replicate it without prior knowledge of the method, and they interbred with Homo sapiens. Repeatedly, the genetic evidence indicates not a single interbreeding event, but multiple episodes of gene flow between Neanderthals and incoming modern human populations, occurring at different times and in different geographic locations across a period spanning tens of thousands of years. This was not a violent encounter between an advanced species and a primitive one. It was a long, complex, geographically distributed relationship between populations that were similar enough to recognize each other as potential mates, and different enough that their offspring carried the genetic signatures of both lineages forward in measurably distinct proportions. And then, in 2021, a paper published in the journal The Innovation by a team led by Qiang Ji of Hebei Geo University described a remarkably complete hominin skull recovered from the city of Harbin in Heilongjiang province in northeastern China. The skull, nicknamed the Dragon Man, was massive, larger than any previously known Homo sapiens cranium, with a brain volume comparable to or exceeding that of modern humans, combined with a robust facial architecture unlike any previously classified hominin. Dating estimates placed it at a minimum of 146,000 years before the present. The research team's phylogenetic analysis suggested that the Dragon Man skull might represent a Denisovan individual, which would make it the first substantially complete Denisovan cranium ever recovered, transforming what had been a species known only from fragments into something with a face, a presence, a physical reality that the handful of teeth and finger bones could never provide. The claim is not yet universally accepted. Other researchers have proposed alternative classifications. The skull is real. The dating is real. The debate about what it represents is ongoing and scientifically legitimate. What it points toward, regardless of its eventual classification, is a picture of human prehistory that is considerably more crowded, more interconnected, and more biologically complex than the simple, linear narrative of modern humans replacing their predecessors ever suggested. We did not simply replace the shadow humans, we absorbed them. Their genes are in our immune systems, helping us fight pathogens our African ancestors had never encountered. Their physiological adaptations are in our high-altitude populations, enabling survival in environments that pure Homo sapiens biology was not originally equipped to handle. Their cognitive capacities, whatever those, were merged with ours in ways that the genomic record records but cannot fully decode. The shadow humans are not entirely gone. In the most literal biological sense, they are still here. In 1963, a joint survey conducted by the University of Chicago and the University of Istanbul passed through the Gurmush mountain range in southeastern Turkey, not far from the ancient city of Şanlıurfa, and noted in its records the presence of a low, rounded hill covered in broken limestone and the occasional fragment of worked flint. The surveyors recorded it as a possible medieval cemetery and moved on. 31 years later, a Kurdish shepherd named Savak Yıldız was walking across that same hill when his foot caught on something protruding from the soil. He reached down and found the top of a large shaped stone rectangular, deliberately worked, unlike anything a natural geological process would produce. He reported it to the Şanlıurfa Museum. The museum contacted the German Archaeological Institute in Istanbul, and in 1994, a German archaeologist named Klaus Schmidt arrived at the site, looked at what Yıldız had uncovered, and made a decision that would occupy the remaining 20 years of his professional life. He started digging. What Schmidt's team uncovered over the following 2 decades, and what the ongoing Taş Tepeler project, sponsored by the Turkish Ministry of Culture and Tourism and involving teams from multiple international institutions, has continued to reveal since Schmidt's death in 2014, is a site so anomalous in its chronological position that it has forced a fundamental reconsideration of one of the most basic assumptions in all of prehistoric archaeology. The site is called Göbekli Tepe. It sits on a limestone ridge in southeastern Anatolia, in a region that is today semi-arid and largely treeless, overlooking the broad plains of the Upper Harran Basin. Its earliest layers have been dated, through radiocarbon analysis of organic material in the fill sediments, to approximately 11,600 years before the present. Its construction and active use appear to have continued through roughly 9,600 years before the present, a span of active occupation and building activity running to approximately 2,000 years. This means that Göbekli Tepe was already ancient by the time the first cities appeared in Mesopotamia. It predates the earliest confirmed agricultural communities in the region by at least 1,000 years. It predates the domestication of wheat, barley, sheep, and cattle, the foundational elements of what we call the Neolithic Revolution, by a margin that, depending on how you define domestication and which site you are using as a reference, runs to somewhere between 500 and 1,500 years. A monumentally sophisticated stone construction complex, built by people who, according to the standard model of human cultural development, should not yet have had the social organization, the surplus labor, the ritual architecture traditions, or the technical capacity to build it. The structures themselves demand description. The most thoroughly excavated portions of Göbekli Tepe consist of a series of circular or oval enclosures, each defined by a ring of large limestone pillars connected by lower stone walls. The pillars are T-shaped in cross-section, a distinctive form that has no clear precedent in any earlier archaeological context. The largest pillars stand up to 5.5 meters tall and have been estimated to weigh between 10 and 20 metric tons each. They were quarried from the limestone bedrock of the surrounding plateau, shaped with flint and obsidian tools, transported to the construction site, and erected with a precision that has impressed every structural engineer who has examined the site in detail. The surfaces of many pillars are carved in low relief, with animal images of considerable artistic sophistication. Foxes, boars, cranes, ducks, scorpions, snakes, spiders, lions, and vultures, rendered with a confident command of form and proportion comparable to the best animal imagery from European cave art of roughly the same period. Several pillars also bear abstract symbols, hands, a belt, items that have been interpreted as garments suggesting that some pillars may represent stylized human figures, a reading supported by the presence of what appear to be arms carved in low relief along the sides of certain T-shaped uprights. 2 central pillars in each enclosure stand taller than the surrounding ring and face each other across the interior space. Whatever these structures were for, and there is genuine, productive disagreement about this, they were not domestic. No hearths, no grinding stones, no storage facilities, no evidence of sustained habitation have been found within the enclosures. The site appears to have been a place people came to, used for purposes that left a distinctive archaeological signature of feasting, animal sacrifice, and structured ritual activity, and then left. Archaeologists have noted one feature of Göbekli Tepe that may be the most genuinely puzzling aspect of the entire site. It was deliberately buried, not abandoned. Not simply left to accumulate natural sediment over centuries. At some point around 8,000 to 9,000 years before the present, the enclosures at Göbekli Tepe were intentionally filled in, packed with a mixture of limestone rubble, flint fragments, animal bones, and soil to a degree, and with a consistency that speaks of organized, purposeful interment rather than gradual decay. The backfill material has been estimated at hundreds of cubic meters per enclosure. Moving and depositing that volume of material required at minimum the same degree of organized collective labor that building the structures had required in the first place. Why a community would invest that level of effort in burying its own ritual architecture, rather than simply ceasing to use it, is a question that has not been answered. One possibility is that the burial was itself a ritual act, a formal closing of the sacred space, a deliberate sealing of whatever the site contained or represented. Another is that the burial was preservational, an intentional act of protection against some anticipated threat or change. A choice to hide rather than abandon. The evidence does not currently distinguish between these or other possibilities. What the deliberate burial did accomplish, whatever its intent, was the extraordinary preservation of the site. The fill material protected the carved pillar surfaces, the delicate low-relief animal images, and the structural integrity of the stone walls across 11,000 years of exposure to weather, seismic activity, and the slow chemistry of soil processes. When Schmidt's team began excavating, they found imagery that was, in places, as crisp as the day it was carved. Now we come to the pillar that has generated the most sustained and consequential interpretive debate. Pillar 43, located in Enclosure D at Göbekli Tepe, is sometimes referred to as the vulture stone. Its carved surfaces include a large vulture with a wing displayed, a scorpion, several other animal figures, and a prominent circular disc that sits above the vulture's wing in a position that some researchers have interpreted as representing the sun or a celestial body. In 2017, Martin Sweatman of the University of Edinburgh's School of Engineering and Alasdair Cowie published a paper in the journal Mediterranean Archaeology and Archaeometry, presenting a detailed statistical analysis of the imagery on Pillar 43. Their argument was that the arrangement of animal figures on the pillar corresponded to a specific configuration of constellations as they would have appeared in the sky above Göbekli Tepe at a date they calculated to be approximately 10,950 years before the present date that falls within the proposed window of the Younger Dryas impact event, the same catastrophic episode that appears in the stratigraphy of the Younger Dryas boundary layer discussed in the megafauna chapter. Sweatman and Cowie propose that Pillar 43 represents a memorial, a carved astronomical record of a specific event in the sky, preserved in stone by people who had witnessed or inherited the memory of something catastrophic and wanted to ensure it was not forgotten. The paper was peer-reviewed and published in a legitimate academic journal. It has also been challenged by other researchers who argue that the correspondence between the carved figures and the proposed constellation positions is not statistically robust, and that the interpretation imposes a modern astronomical framework onto imagery whose original meaning cannot be verified. This is a legitimate methodological objection, and it has not been definitively resolved. What remains unexplained is the degree of astronomical sophistication that would be required to produce the site at all, independent of any specific interpretation of Pillar 43. The orientation of the enclosures at Göbekli Tepe, analyzed by several independent research teams, shows consistent alignment with celestial reference points in ways that appear deliberate rather than incidental. The builders of these structures were, at minimum, careful observers of the sky, which should perhaps not surprise us, given that careful celestial observation has been documented in Ice Age contexts reaching back tens of thousands of years earlier. As we examined in the cave art chapter, the most thoughtful version of the theoretical framework surrounding Göbekli Tepe, the one held with appropriate caution by several researchers working on the broader Taş Tepeler project, is that the site represents a response to catastrophe rather than an expression of established prosperity. One theory suggests that Göbekli Tepe was built not by a community that had achieved surplus and stability, but by communities that had lost both groups of hunter-gatherers displaced and destabilized by the rapid ecological transformation of the Younger Dryas period, who came together at a recognized high place to perform ritual acts that addressed, in whatever symbolic vocabulary they possessed, the disorientation of a world that had abruptly and violently changed. If that reading is correct, then Göbekli Tepe is not evidence that civilization predates agriculture. It is evidence that catastrophe precedes civilization, that the impulse to build something permanent, to organize collective labor around a shared symbolic purpose, to mark time and loss and cosmic uncertainty in durable stone, emerges not from comfort and surplus, but from displacement and grief. The hill had been waiting for 31 years between its first survey notation and Klaus Schmidt's shovel, and only 5% of it has been excavated. Whatever remains beneath the surface of that limestone ridge in southeastern Turkey is still, in the most literal sense, buried, undisturbed, silent. There is a crossing that should not have been possible. 65,000 years ago, a group of human beings stood at the edge of a coastline somewhere in what is now Indonesia or the Malay Peninsula and looked out across open water. Not a narrow strait, not a river crossing, open ocean, a minimum of 80 kilometers of deep, unpredictable, predator-filled sea stretching between the edge of the Sunderland landmass and the nearest landfall of what is now the Australian continent. Even at the lowest sea levels of the last glacial maximum, that crossing required the deliberate construction of watercraft capable of carrying enough people to establish a viable founding population, the navigational knowledge to maintain a direction across open water without landmarks, and the organizational capacity to coordinate a migration of sufficient scale to succeed. They made it. We know this because of a site called Majid Bebe, a rock shelter located in the Northern Territory of Australia near the edge of what is now Kakadu National Park. In 2017, a team led by Chris Clarkson of the University of Queensland published findings in the journal Nature, reporting the results of new excavations and revised dating analyses at Majid Bebe that pushed the confirmed human occupation of Australia back to at minimum 65,000 years before. The present. The dating used optically stimulated luminescence, a technique that measures the last time individual grains of sand were exposed to sunlight, applied to sediment layers containing stone tools, ground ochre, and other unambiguous signatures of human presence. 65,000 years. This means that Homo sapiens reached Australia, a continent requiring open ocean crossing to access under any reconstructed sea level scenario before they reached Europe, before they reached the Americas by tens of thousands of years. At a time when Neanderthals were still the primary inhabitants of the European continent, and Denisovans were ranging across Asia. The people who made that crossing were not tentative explorers feeling their way cautiously along coastlines. They were experienced maritime travelers operating in an environmental context that demanded sophisticated watercraft technology and accumulated navigational knowledge. Whatever those boats looked like, and we have no direct evidence, since organic materials from 65,000 years ago in tropical conditions do not survive. They worked. The founding population of Australia crossed open ocean, established themselves on a continent they had never seen, and gave rise to the longest continuously maintained cultural tradition in human history. Australian Aboriginal cultures represent an unbroken line of cultural transmission, stretching from that initial crossing to the present day. 65,000 years of accumulated knowledge, ceremonial practice, and relationship with country. The migration story in Australia is, in certain respects, the clearest example of a pattern that appears repeatedly across the global record of Ice Age human dispersal. Humans consistently went further, earlier, and across more formidable barriers than the standard model of cautious, gradual migration predicted. The out-of-Africa dispersal itself, in its second and most consequential wave beginning somewhere around 70 to 80,000 years before the present, appears to have followed a coastal route along the southern rim of Asia rather than a northern overland path through the Levant. This coastal highway model, developed and argued extensively by Stephen Oppenheimer in his work Synthesizing Genetic and Archaeological Evidence, proposes that the primary dispersal pathway ran along the coastlines of what are now the Arabian Peninsula, the Indian subcontinent, and Southeast Asia environments that offered consistent access to marine food resources and would have supported relatively rapid movement by populations already adapted to coastal living. The problem with confirming this model archaeologically is the same problem we encountered in the chapter on drowned continents. The coastlines of 70,000 years ago are underwater. The sites where the earliest coastal migrants camped, fished, and buried their dead are sitting beneath the Indian Ocean and the South China Sea, inaccessible to conventional excavation. The coastal highway hypothesis is supported by genetic evidence from modern populations and by the logic of migration ecology, but its physical archaeological record is largely beyond current reach. What we can access are the endpoints, the places where the migrants arrived and left signatures in sediment layers that have remained above water and in conditions favorable to preservation. And those endpoints tell a story of movement so extensive and so rapid by the standards of Pleistocene population dynamics that it has repeatedly required upward revision of the timeline as new dating techniques have been applied to existing evidence. Now move to the other side of the world. The question of when and how humans first entered the Americas has been one of the most persistently contested problems in all of prehistoric archaeology, and it remains so today. The traditional model known as the Clovis first hypothesis, named after the Clovis culture identified at a kill site near Clovis, New Mexico in the 1930s, proposed that the first Americans arrived approximately 13,000 years before the present via the Bering Land Bridge and an ice-free corridor that opened between the Laurentide and Cordilleran ice sheets as they began to retreat. The Clovis first model was the mainstream consensus for decades. It has been substantially dismantled by accumulating evidence from multiple sites across North and South America. Tom Dillahay of Vanderbilt University spent years excavating Monteverde, a site in southern Chile that sits more than 15,000 kilometers south of the Bering Land Bridge. The archaeological layers at Monteverde, which include wooden structures, plant remains, animal bones, and stone tools in clear stratigraphic association, have been dated to approximately 14,500 years before the present, making the site older than Clovis, and so far south that any migration model requiring a land corridor through the ice would struggle to account for it. Then, in 2021, a paper published in the journal Science by Matthew Bennett of Bournemouth University and colleagues reported the discovery of fossilized human footprints at White Sands National Park in New Mexico, preserved in ancient lake sediment and dated using seeds found within the same sediment layers to between 21,000 and 23,000 years before the present. If those dates hold under further scrutiny, and they have been challenged on methodological grounds, with the debate ongoing, they place humans in the interior of North America at the peak of the last glacial maximum, at a time when the conventional ice-free corridor model says passage from Beringia to the south was physically blocked. The most coherent explanation for the accumulating pre-Clovis evidence is the Kelp Highway hypothesis, developed and advocated most prominently by John Erlandson of the University of Oregon. Erlandson's model proposes that the initial entry into the Americas did not come through an interior land corridor, but along the Pacific coastline, a route that would have been navigable by watercraft using coastal peoples even during the glacial maximum, following the productive kelp forest ecosystems that ran along the North Pacific Rim from Japan through the Aleutians and down the western coast of North America. People already adapted to maritime coastal living, moving along a coastline that offered consistent food resources, could have reached the southern tip of South America faster than interior migrants moving through an ice-free corridor that was, for much of the relevant period, ecologically marginal and resource poor. One theory, supported by an emerging body of ancient genomic evidence, suggests that the peopling of the Americas was not a single migration event, but a complex, multi-wave process extending over thousands of years, involving at minimum 2 and possibly 3 or more distinct founding populations arriving by different routes at different times. The genetic diversity of Native American populations, particularly in South America, contains signals that have proven difficult to explain with a single wave model. Specific populations in the Amazon basin and along the Pacific coast of South America carry genomic signatures that appear more closely related to Australasian populations than to the Siberian-derived ancestry that dominates most. Native American genomes, a finding first reported by Pontus Skoglund and David Reich of Harvard Medical School in 2015, and since confirmed and extended by multiple independent research groups. What this signal means in terms of actual migration events is not yet resolved. It does not require a direct transoceanic crossing from Australia or Melanesia. It is consistent with a migration route through Asia that passed through or near populations carrying Australasian-related ancestry, before eventually reaching the Americas through Beringia or the Kelp Highway. But the signal is real. It is documented in peer-reviewed literature, and it adds a layer of complexity to the Americas migration story that the standard single-wave Beringian model cannot accommodate. What remains unexplained is the full identity of the Kennewick Man, or the Ancient One as he is known to the confederated tribes of the Columbia Plateau, a remarkably complete skeleton recovered from the banks of the Columbia River in Washington state in 1996, dated to approximately 9,000 years before the present, and the subject of a decade-long legal and scientific dispute over custody and analysis rights. Genomic analysis eventually confirmed that the Ancient One was most closely related to Native American populations, not to any Asian or European group. But his cranial morphology, which had initially prompted speculation about non-Native American ancestry, remains an area of active research into the range of physical variation present in the earliest American populations. The migration story, taken as a whole across its global arc from the first African coastal dispersal, through the open ocean crossing to Australia, across the Ice Age landscapes of Eurasia, through Beringia, and down the length of 2 continents, is not a story of cautious, gradual expansion into empty space. It is a story of relentless, purposeful, technically sophisticated movement across every barrier the planet placed in front of them, without maps, without metal, without any of the navigational or logistical infrastructure that modern humans assume is required for journeys of this scale. They went anyway, and in going, they became the first and only species in the history of life on Earth to establish a sustained presence on every habitable landmass on the planet, before the invention of writing, before the founding of the first city, before any of the developments that conventional history treats as the beginning of human achievement. The achievement had already happened. It happened on the water, in the dark, 65,000 years before anyone thought to write it down. Imagine you are alive 12,900 years ago. The worst of the ice is behind you. The glaciers have been retreating for several thousand years. The world is warming, slowly but perceptibly, the kind of change that accumulates across generations, so that your grandchildren's world is measurably greener and warmer than the world your grandparents described. Megafauna populations are thinning, but game is still available. Sea levels are rising, swallowing familiar coastlines. But the process is gradual enough that communities can move. The long frozen grip of the last glacial maximum is loosening, and then, within the span of a single human lifetime, possibly within a decade, the temperature across the northern hemisphere drops by somewhere between 10 and 15 degrees Celsius. Rivers freeze that had not frozen in living memory. Forests that had been slowly advancing northward stop and retreat. The grasslands that had been expanding across Central Asia contract. Glaciers that had been melting stabilize and begin to advance again. The growing season shortens by weeks, then months. Animals that had begun to move into newly available territory are pushed back. Human communities that had been adapting to a warming world are suddenly contending with conditions more severe than anything their recent ancestors had experienced. This is not a gradual climate shift. The Greenland ice cores, drilled and analyzed by teams including those from the Niels Bohr Institute in Copenhagen and the US National Science Foundation's GISP project, record the onset of the Younger Dryas with a resolution that is almost impossible to process calmly. In certain sections of the ice core record, The transition from the warming interstadial period to full Younger Dryas conditions appears to have occurred within decades. Some analyses suggest the critical threshold may have been crossed within a single human generation. In geological terms, this is not a transition, it is a switch. The Younger Dryas lasted approximately 1,200 years, from roughly 12,900 to 11,700 years before the present. When it ended almost as abruptly as it had begun, with some researchers arguing the final transition took as little as 1 to 3 years at its most acute phase. 1,200 years of renewed glacial conditions, beginning and ending within a human lifetime. The mechanism most widely accepted by mainstream climatology for triggering the Younger Dryas involves the disruption of the Atlantic meridional overturning circulation, the same deep ocean current system whose sensitivity to freshwater input was established by the Heinrich event record discussed earlier. As the Laurentide ice sheet began to melt in earnest following the last glacial maximum, it generated enormous volumes of fresh meltwater that accumulated in vast proglacial lakes across North America. The largest of these, Lake Agassiz, sat across what is now Manitoba, Ontario, and the northern Great Plains, and at its maximum extent covered an area larger than all of the modern Great Lakes combined. At some point, around 12,900 years before the present, a drainage pathway opened, possibly through the St. Lawrence River system, possibly through Hudson Bay, and an enormous pulse of cold fresh water flooded into the North Atlantic. Roger Fairbanks of Columbia University's Lamont Doherty Earth Observatory documented the signature of this meltwater pulse in coral records from Barbados. Published in 1989, identifying an episode of extraordinarily rapid sea level rise, Meltwater Pulse 1A, that corresponds in timing to the Younger Dryas onset. Fresh water is less dense than salt water and does not sink in the same way. When enough of it floods into the North Atlantic, it can cap the surface waters and prevent the deep convective sinking that drives the thermohaline circulation. When that circulation slows, the heat transport that keeps northwestern Europe anomalously warm for its latitude stops. The temperature drops. The ice advances. This is the conventional explanation, and it is well supported by multiple independent lines of evidence. But the conventional explanation does not fully account for everything that happened at the Younger Dryas boundary. In 2007, Richard Firestone of Lawrence Berkeley National Laboratory and a large consortium of co-authors published a paper in the Proceedings of the National Academy of Sciences presenting evidence for what they called a Younger Dryas impact event, a cosmic collision or atmospheric explosion involving a fragmented comet or asteroid over the North American ice sheet, approximately 12,900 years before the present. The evidence they presented included elevated concentrations of platinum and iridium in sediment layers at the Younger Dryas boundary at multiple sites, microspherules and magnetic spherules consistent with high-temperature melting of surface material, nanodiamond particles requiring formation under extreme pressure conditions, and a layer of amorphous carbon and charcoal interpreted as evidence of massive wildfires triggered by the impact. The most significant challenge to the impact hypothesis has been the difficulty of replicating specific evidence at specific sites. Some research groups have confirmed the anomalous markers, others have failed to find them at comparable sites, or have proposed alternative explanations for the materials present. The scientific community has not converged on a consensus. What has not been explained away is the correlation between the Younger Dryas boundary and a specific layer found at Clovis archaeological sites across North America, a dark, carbon-rich stratum known informally as the black mat. At site after site where Clovis age material has been excavated, the same pattern appears. Below the black mat, the bones of extinct megafauna and Clovis stone tools. Above it, neither. The black mat appears to represent a rapid environmental transition, a moment when the ecological conditions that had supported Clovis hunting culture and the remaining megafauna populations simultaneously ceased to exist. Whether that transition was triggered by a cosmic impact, by the meltwater-driven climate reversal, or by some combination of both, is what remains unexplained. The black mat is real. The abrupt termination of the Clovis cultural signature beneath it is real. The simultaneous disappearance of the remaining North American megafauna at roughly the same stratigraphic horizon is real. A confluence of real, documented phenomena at a single moment in time that has not been fully explained by any single mechanism proposed to date. Across the world, in cultures separated by oceans and continents, there are stories of a great flood, a deluge that covered the known world, a catastrophic inundation from which a small remnant of humanity survived to rebuild. These narratives appear in the Epic of Gilgamesh, written in cuneiform on clay tablets in ancient Mesopotamia. They appear in the Hebrew Bible. They appear in the flood mythology of the Ohlone people of California, the Hopi of the American Southwest, the Yoruba of West Africa, the Aboriginal peoples of Australia, the Vedic traditions of the Indian subcontinent, and more than 200 other documented cultural traditions around the world. Archaeologists have noted, carefully and without invoking supernatural causation, that the geological record of the period between roughly 15,000 and 7,000 years before the present contains multiple documented episodes of catastrophic sea level rise, glacial lake outburst floods, and coastal inundation events of a scale and rapidity that would have been experienced by affected populations as precisely the kind of world-ending deluge these narratives describe. The flooding of the Black Sea Basin, proposed by William Ryan and Walter Pittman of the Lamont Doherty Earth Observatory in their 1997 hypothesis, would have inundated a freshwater lake basin the size of a small sea within a geologically brief period, as Mediterranean waters broke through the Bosphorus threshold. The submersion of Doggerland, the drowning of Sunderland, Meltwater Pulse 1A, each of these events was real, documented in the geological record, and would have been catastrophic for human populations living in the affected regions. One theory, held by a growing number of researchers working at the intersection of geology, climatology, and cultural anthropology, suggests that the widespread flood narratives preserved in world mythology represent fragmented but genuine cultural memories of real inundation events transmitted orally across hundreds of generations, transformed and elaborated by each culture that carried them, but retaining at their core the preserved memory of a time when the world as people knew it was swallowed by water. This is not a fringe position. It is a scientifically legitimate hypothesis that has been discussed in peer-reviewed contexts, including work by Patrick Nunn of the University of the Sunshine Coast, whose research on Aboriginal Australian oral traditions has identified what he argues are preserved memories of specific coastal inundation events that can be geologically dated to between 7,000 and 10,000 years before the present. But the Younger Dryas is more than a catastrophe. It is, in a profound and perhaps counterintuitive sense, a creation event, because it was in the immediate aftermath of the Younger Dryas, in the warm, ecologically disrupted, demographically stressed world that emerged when the climate finally stabilized around 11,700 years before the present, that agriculture appeared. Not in one place, independently discovered by a single brilliant community, but in multiple locations, across multiple continents, within a few thousand years of each other: the Fertile Crescent, the Yellow River Valley, the highlands of New Guinea, Mesoamerica, the Andes. In each of these regions, the domestication of plants and animals, the transition from foraging to farming that we call the Neolithic Revolution, began within a geologically brief window following the end of the Younger Dryas. One theory, articulated most comprehensively by researchers including Ofer Bar Yosef of Harvard University, suggests that this near-simultaneous agricultural transition across multiple continents was not coincidental. The Younger Dryas had disrupted the ecological conditions that supported mobile foraging lifestyles, compressed human populations into refugia, and forced communities to manage food resources with an intensity and deliberateness that crossed the threshold into active cultivation. When the climate stabilized, the knowledge and the necessity were both in place. The catastrophe did not end civilization. It built it. The suffering of 1,200 years of renewed cold and ecological disruption produced, in its aftermath, the sedentary communities, the managed landscapes, the stored surpluses, and the social complexity that would eventually give rise to everything we recognize as the ancient world. Göbekli Tepe sits at the hinge of this transition built by people living through the immediate aftermath of the Younger Dryas, encoding in stone their response to a world that had twice within recent cultural memory, been utterly transformed by forces beyond any human capacity to predict or prevent. They built temples because the ground had stopped being reliable. They reached for permanence because everything impermanent had already been taken from them. In 2023, a paper published in the journal Nature announced the discovery of the oldest known wooden structure on Earth. Not stone, not bone, not fired clay, wood. The structure was found at Kalambo Falls, a site on the border between Zambia and Tanzania, where the Kalambo River drops over a spectacular escarpment into a gorge before continuing toward Lake Tanganyika. The site had been known to archaeologists since the 1950s and had yielded important finds over the decades, but the application of new luminescence dating techniques to material recovered during fresh excavations produced a result that the research team, led by Larry Barham of the University of Liverpool, described in careful, measured academic language as significantly older than expected. The wooden structure dated to at least 476,000 years before the present. 476,000 years. This is not simply older than any previously known wooden construction. It is older than Homo sapiens as a species. The individuals who shaped and joined those logs using stone tools to notch and interlock the timber in a way that served a clear structural purpose, creating what appears to have been a raised platform or the foundation of a dwelling belonged to an earlier hominin species, most likely Homo heidelbergensis, who preceded modern humans in Africa and Europe, and are considered a likely common ancestor of both Homo sapiens and Neanderthals. The find at Kalambo Falls does not simply push a record back. It fundamentally reframes the question of when purposeful, planned construction behavior appeared in the human lineage. It suggests that the cognitive capacities required for structural engineering, the ability to visualize a three-dimensional object, plan the sequence of steps required to produce it, and coordinate the physical work of construction, were present in our ancestors, not 40,000 years ago, not 100,000 years ago, but nearly 500,000 years ago. And yet we did not know this until 2023. Why? The answer to that question is not simple, and it is not a story of institutional suppression or deliberate concealment. It is a story of something more mundane and in some ways more troubling: the systematic, structural, entirely non-conspiratorial ways in which the archaeological record fails to represent the full reality of human prehistory. Begin with the most basic problem. Wood rots, fiber dissolves, leather decomposes, plant material, textile, cordage, basketry, worked hide, all of the organic materials that human communities depend on for the majority of their daily material culture survive in the archaeological record only under exceptional conditions. Extreme cold, extreme aridity, waterlogging in anoxic sediment, or enclosure in sealed deposits can preserve organic material across long timescales. Normal conditions of temperature, humidity, and biological activity cannot. This means that everything ancient humans made from organic materials, which is to say, the overwhelming majority of what they made, has vanished. What survives is stone, fired ceramic, bone, and shell. The archaeological record that forms the evidential foundation of our understanding of human prehistory is not a representative sample of past human material culture. It is the durable fraction of that culture, systematically biased toward materials that happen to resist decay. Consider what this means in practical terms. The Kalambo Falls structure survived because it was preserved in waterlogged sediment in a specific depositional context that inhibited the normal biological processes of decay. Had it been deposited under ordinary conditions, it would have been gone within centuries. Every other wooden structure built by Homo heidelbergensis across Africa and Eurasia over hundreds of thousands of years is gone, not because it was not built, but because wood does not last. The second structural bias is geographic. The classic image of Paleolithic archaeology is the cave site dark chambers in limestone hills, where ancient humans sheltered, where bone and stone and pigment were deposited in sealed, stratified layers that preserve the sequence of occupation across tens of thousands of years. Cave sites are extraordinary archives. They have yielded some of the most important evidence in all of prehistoric archaeology, but they represent a profoundly specific subset of ancient human behavior, the subset that happened to take place in limestone cave systems. Most of the Earth's surface does not have limestone caves. The vast majority of the inhabited ancient world, open grasslands, river valleys, coastal plains, tropical forests, leaves archaeological signatures that are far more difficult to detect, more vulnerable to erosion and agricultural disturbance, and less likely to be encountered by researchers than the dramatic, well-defined stratigraphy of a cave deposit. The result is a record that overrepresents certain geographic zones, Western Europe, the Levant, parts of southern Africa, and dramatically underrepresents others, including most of tropical Africa, most of South and Southeast Asia, and virtually the entire expanse of the world's tropical forests. 90% or more of the tropical forest floor has never been subject to systematic archaeological survey. The reasons are practical: dense vegetation, difficult access, limited funding, competing research priorities rather than ideological, but the effect is the same. We are constructing our understanding of ancient human behavior from a sample that excludes most of the geographic range in which ancient humans actually lived. Archaeologists have noted for decades that the Upper Paleolithic Revolution, the apparent sudden flowering of symbolic behavior, art, and technological sophistication in the European record, beginning around 45,000 to 50,000 years before the present, is increasingly difficult to interpret as a genuine cognitive threshold rather than an artifact of the geographic distribution of archaeological research. Chris Henshelwood of the University of Bergen and his colleagues, working at Blombos Cave in the Western Cape of South Africa, have documented ochre engravings, shell bead ornaments, and sophisticated composite tool manufacturing at Blombos, dating to 75,000 years before the present, 30,000 years before the supposed European Revolution. The Stilbay and Howizens port industries of southern Africa represent episodes of advanced symbolic and technological behavior, dating to between 65,000 and 80,000 years before the present. What remains unexplained, and what constitutes one of the genuine intellectual puzzles of Paleolithic archaeology, is why this behavioral sophistication appears, reaches a peak, and then seems to fade in the African record before reappearing, rather than emerging once and spreading continuously. The pattern has been interpreted by some researchers as reflecting real oscillations in population size and cultural transmission capacity, periods when African populations contracted due to drought or other environmental stress, losing the critical mass required to maintain complex cultural traditions, then rebounded and rebuilt them. The Toba supervolcano eruption, dated to approximately 74,000 years before the present, and centered on what is now Lake Toba in Sumatra, has been proposed as one such bottleneck event. Stanley Ambrose of the University of Illinois at Urbana-Champaign argued in 1998 that the Toba eruption triggered a volcanic winter of sufficient severity to dramatically reduce global human populations, possibly to as few as 10,000 to 30,000 individuals, creating a genuine near-extinction event followed by rapid population expansion from a small founding group. This population bottleneck hypothesis has been influential and widely discussed, but it has also been challenged by more recent genetic analyses and by African archaeological evidence that shows cultural continuity through the Toba horizon at some sites, suggesting that the bottleneck, if it occurred, was not uniformly catastrophic across all regions. The debate is not resolved. What it points toward is a picture of human prehistory that is far more episodic, far more regionally variable, and far more susceptible to catastrophic interruption than the smooth progressive narrative of continuous cognitive and cultural development implies. Now consider what has changed in the last 15 years, and what it suggests about how much of the past remains to be discovered. LiDAR light detection and ranging is an airborne remote sensing technology that fires laser pulses toward the ground and measures the return times with sufficient precision to reconstruct detailed, three-dimensional maps of surface. Topography beneath vegetation cover. Applied to archaeology, it has produced a series of revelations so significant that the field has had to develop new conceptual frameworks to process them. In 2011, Arlen Chase and Diane Chase of the University of Central Florida applied LiDAR survey to the Maya lowland site of Caracol in Belize and revealed, in a single survey campaign, more architectural and agricultural infrastructure than decades of ground-based mapping had identified. In 2013, Damien Evans of the École Française d'Extrême-Orient led a LiDAR survey of the Angkor region in Cambodia. that revealed the full extent of the medieval Khmer urban landscape surrounding Angkor Wat, an interconnected city covering more than 1,000 square kilometers, making it one of the largest pre-industrial urban complexes ever documented. In 2018, a consortium of researchers using LiDAR across northern Guatemala identified more than 60,000 previously unknown Maya structures across an area of more than 2,000 square kilometers, fundamentally revising estimates of Maya population density and social complexity during the Classic period. These are not Ice Age discoveries, but they establish the principle with unmistakable clarity. The ground contains vastly more than we have found. The limiting factor has not been the absence of evidence, but the absence of the tools capable of detecting it. Applied to the Pleistocene and early Holocene record, the LiDAR principle implies a vast reservoir of undiscovered sites, structures, settlements, earthworks, landscape modifications that exist beneath the vegetation cover of the world's forests, beneath the sediment of river floodplains, beneath the waters of shallow coastal shelves, waiting for technologies and research programs capable of reaching them. One theory, which sits within the mainstream of archaeological methodology, even if its full implications remain underexplored, suggests that the human cognitive and organizational capacity we associate with the emergence of civilization, the ability to plan at scale, to manage complex social hierarchies, to modify landscapes deliberately for long-term purposes, was present far earlier than the current record demonstrates, and that the gap between capacity and documentation is primarily a gap of preservation and survey coverage, rather than a gap of actual human ability. The oldest known wooden structure is 476,000 years old. It was found in 2023. It had been lying in the sediment at Calambo Falls for nearly 500,000 years, preserved by the specific chemistry of waterlogged soil, waiting for a research team with the right dating technology and the funding to apply it. How many structures equally ancient, equally significant, are lying in sediment that no research team has yet reached? The honest answer is that we do not know. And the more carefully you look at the structural biases of the archaeological record, the preservation bias, the geographic bias, the survey coverage bias, the funding bias that directs research toward regions with established academic infrastructure and away from those without, the more clearly you see that what we know about the human past is not the whole story. It is the fragment that survived the conditions. The rest is still buried, still waiting, still, in the most literal and unmetaphorical sense of the word,